On now.
Okay. We still have a few minutes. And touch button, or it's not really a button, whatever it is, and have the red light lit while you're asking your question. So welcome everyone. Now's the official part of our presentation. So again, my name is Jennifer Dill. I'm a faculty member here in Urban Studies and Planning. And along with my colleagues, Chris Monsieur from Civil Engineering and Rob Bertini, who's in Civil Engineering and Urban Studies and Planning, we help co-organize this weekly Friday seminar series. And today we have a special guest, a visiting scholar with us, and the visiting scholar program is sponsored by ODOT. So I want to thank our ODOT partners who have helped us to bring scholars from outside of the area to come with us and share a lot of very interesting transportation topics. So without further ado, I want to introduce Professor Emeritus Ken Small, who is at University of California at Irvine. He's Professor Emeritus of Economics at UC Irvine, who specializes in urban transportation and environmental economics. He's served many years as editor of various journals. He's served on many National Research Council panels, in addition to consulting for many different organizations. And generalizing on his very good bio here. And recently, he's previously served as chair of economics and associate dean of social sciences at UC Irvine. So without further ado, I want to turn it over to Ken, and I will remind you again to use the microphones when you do ask questions.
Well, thank you very much. And it's very exciting to talk at Portland State. I did this 10 years ago or so. But to talk at an urban center that has such a diverse group of people. It's also challenging, as you can imagine. Economists always or other people are always afraid that economics is going to be over their head or too mathematical. And this does have some mathematics, but I'll try to speak it in English as I go. But I really always like having a diverse audience, and particularly when there's people who evidently want to see if they can extract something useful in the real world out of this, which is something I aim for in my research. I hope I succeed, at least sometimes. So this obviously has real world, a real world title, so we'll see whether we succeed in that. This is joint work I've done with Ian Perry at Resources for the Future, which is a environmental think tank in Washington, D.C. And it kind of grows out of some work that he's done, and one part of it that he and I have done, on, you might say, public finance models that try to capture how public policies, particularly pricing policies like transit pricing or gasoline taxes or things like that, how they can capture some of the many aspects of urban problems that make them so interesting, and transportation problems that make them so interesting to economists and to others. In particular, spillovers, or what we call externalities in the jargon. And of course, people have not been unaware of this in the area of public transport. And so we're certainly not doing anything new to talk about transit subsidies. Here are some of the rationales that have been suggested for transit subsidies, and often one at a time. External costs of driving. In other words, let's get people out of their cars and into transit. And does this work if I... Yeah, it does. So congestion, of course, is the one that people are most familiar with. But it might save you on some traffic accidents, injuries and deaths, and of course it might reduce air pollution. So that's a kind of a diversion rationale to use transit to try to get people off of another mode that has a lot of problems associated with it. And of course, I'm preaching to the choir when I talk to people in Portland about trying to do things about automobile pollution and congestion and so forth using public transit. And as I'm sure you well know, there are lots of problems in doing this in practice. For example, the build it, they will come scenario has great controversy about just how effective that is. So a similar thing applies here. If you build it, that is, if you build public transit and price it below cost, will that help divert more cars than otherwise would from the highways? So we try to give some actual estimates of that. So you'll see that. So that's buried inside these equations, and I'll try to make it clear to you if it's not apparent. Another, which is probably less familiar to a lot of people, is scale economies due to waiting time. These are sometimes called mooring effects, after my friend and occasional colleague at Irvine. He has been visiting at Irvine from time to time since he retired at University of Minnesota, but he was a professor of economics at University of Minnesota. And he observed in a kind of a formal, analytical way, what maybe was apparent to other people in a more informal way, that it gets cheaper to operate transit if lots of people are riding it. That is, cheaper per person. That might seem obvious to you, but of course it would not be true if there were just fixed-size transit vehicles and they always carried a certain number of people, and every new rider required another, 1/40th of a bus or something like that. So working out exactly what that means is a different thing. But in terms of the economics of it, and in particularly in terms of rationale for how you do transit pricing, the implication is if you think of the cost function for providing transit as including not only the cost to transit providers, but also the cost to the users, and you treat their waiting time, in vehicle time too, but it's mostly the waiting time or the walking time to a transit stop, as part of their cost. And indeed, there is lots of economics research on this. We know that people do place a high value on those. In fact, quite a bit higher than they do sitting in the vehicle. Most people apparently are not like me. I'd rather be out walking, even in this weather, than sitting. But apparently, people do value that, and it's particularly, I think, waiting at a transit stop, because sometimes the conditions are not that comfortable. So if you count that as part of the cost, then what you get is, because people's waiting times and or walking times are reduced, the more frequent the transit service is. As you get more passengers and you increase the service at some level, not necessarily proportionally, to handle them, you reduce the user costs, and you can trade those off against the agency costs and come up with a cost function which you can minimize. In other words, you can choose the optimal type of service for the transit agency to offer that will minimize that function. And that's implicit in our framework. The reason economists like to think of that as scale economies is analytic. You can put it into the cost function and do things with it, but then you can take the next step, which is talking about pricing, because there's lots of economic modeling that suggests under certain conditions it would be ideal to price at marginal cost. That is, you price not at the average cost for serving the user, but at the additional cost for serving an additional user. And you get that out of it. If you do the cost function the way I've just described, you get a marginal cost out of that. And whenever you have scale economies in a cost function, you know that the marginal cost is below average cost. Therefore, you would subsidize if you follow that marginal cost pricing rule. Now, there may be other reasons why you wouldn't want to do that, and I'm not really going to go into them today very much, but there are practical considerations. Of course, subsidies require raising taxes, and they have their own costs, and there are political costs, if you will, to this, because people may not trust that the taxes will be spent wisely, and so forth. And then there is the whole question about whether it's better to provide transit by public or private operators. There's some evidence that public operators, as you give the agencies subsidies, their costs tend to go up. Some of it is because they're more generous to their employees. There may be other reasons too. And so that could be a consideration. And if you are a believer in the value of privately provided transit, that might be a counterweight, because maybe you would decide it's worth living with a non-optimal price for transit in order to have the private operators standing on their own feet and not being subsidized. On the other hand, you can have privately provided transit and give a user-side subsidy, give a subsidy basically per user, and so you can have both worlds. So I'm not going to deal with in this talk with the private-public thing or with the politics of it, but just to try to find the implications of what these different things would mean for optimal transit pricing and therefore optimal subsidies. So there have been a number of recent estimates, some of them not so recent, 1978, and they're all over the map. And it's partly because some of them take some but not all of these different factors into account. So Glaister and Lewis is a very well-known one. They were at London School of Economics, I think. Glaister, I believe, is now at Imperial College in London, and David Lewis is at a consulting firm in Canada and Washington. So they got one result, which suggested optimal subsidies. Vitan, a cohort of mine in graduate school at Berkeley, did a model where he was, I think, was just dealing with the scale economies, not with these other. In fact, I don't think either of these papers, if I remember right, deals with the congestion accident. I'm sorry, maybe Glaister and Lewis do. Vitan is just dealing with the scale economies, and he gets a fare essentially zero. This was applied to San Francisco. That might raise your your eyebrows. So Winston and Shirley, who this is Clifford Winston at Brookings Institution, he is a big privatization advocate, and he's a real skeptic about public provision of a lot of things. They got a result that the subsidy should be near zero. In other words, the fare should be near average cost. Some researchers in Belgium, Bruno de Borger and several colleagues, did several different things. And you can see now we're getting down to more fine points. They considered alternate assumptions about how the transit agency responds to additional patronage that might be brought in by lowering their fare. Do they provide service proportionally? And service here means vehicle miles. So in other words, do they add new vehicles in the same proportion that the patronage goes up? So that's one case, and the other extreme is no service adjustment. In other words, you just let more people get on the same vehicles and be more crowded. So you get rather different results from that. We're going to do a model that allows for these as a special case, but actually it allows for any intermediate amount of service adjustment, and I have one that I propose as something close to what you would get if you did the optimization that I was describing a minute ago. That is, if the agency is optimizing by, maybe I shouldn't use that word, just minimizing the total cost to itself and its users, as though that they did not distinguish the two. Van Dender and Prost, also in Belgium. Van Dender is now at Irvine, actually. He's my colleague. But at this time he was in transition. They got, again, some rather distinctly different results depending on what you assume. First best, in this case, means taking into account all of these externalities. So they got, no, I'm sorry, my mistake. First best means that you're able to price automobiles at an ideal optimum, and therefore there is no more external cost of driving because that's already taken into account by drivers. So that's of course, there's no place in the world that does that. London is making an attempt at something like that in a very rough way, and Singapore has pricing it at Center City. But so this is more of a theoretical right. So then a theoretical result. So they get the fares would be then much higher. In other words, if you could price the cars, this top rationale would go away, and the scale economies rationale, according to their work, would not be enough to justify much of a subsidy. I haven't said whether there is a subsidy, but at least compared to current fares in Belgium, they should be higher. But when you take into account second best, that is to say, what I'm talking about here, the fact that the roads are not priced and probably not going to be at anything like optimum, and therefore we do have congestion externality, then you get, a very split result. In the peak period, you get practically zero fares. So that's like Vitan got. In the off-peak, you get fares quite a bit higher than that. So we also, in our work, will have peak and off-peak separated. So we would have the potential to get a result like that, although we don't get such a large distinction. So what we add to the studies that have been done before are that in addition to I called it here scale economies due to waiting time. I think that's how Mooring and Glacier and Lewis and most others have modeled it. We also account for the fact that the transit agency can not only add more service to existing routes, but it could add more routes. So it can increase the route density. That will affect people's walking time. In general, you could say access time, that is, how easy it is for people to get to a transit line. I'm just going to call it walking time for simplicity, so that I'm not dealing explicitly with a park and ride or a kiss and ride type of mode. But so just think of people living in an area and walking to the nearest transit stop. And so I'm going to allow for that. We're going to take explicitly crowding into account so that if the vehicle is not full and the transit agency responds by letting the load factors go up, that is more passengers per vehicle, that creates some crowding, and we're going to take the cost to the users of that crowding into account. I would have to tell you up front, this is kind of the weakest point at this point in our empirical parameters, is trying to figure out how to measure that. And then finally, we're also going to take into account bus size. So you have to think of this as a bit of a long-run response that we're talking about, where if the transit agency decided to lower its fares and that brought in more passengers, as well as adding more routes or adding more vehicles, it could also just use bigger vehicles. That has a cost, and there are some estimates of that. I think they're from Britain, the ones that we use. And so we allow for that as well. So you can see this is a bit of a complicated model because we're really trying to reconcile these various results by having a model that will take in all the major effects. Trying not to make it too complicated, and this paper has been a long time in the works, and one reason is we keep looking for ways to simplify it, to simplify the exposition and the notation. What you're getting here is actually not the latest. We've done another round of trying to make it even simpler to explain, but we haven't written that up yet, so I didn't try to present that. But the key thing is we're using a single analytical model that incorporates all of these at once, and I think you'll see a certain amount of symmetry to it. And then we've tried to look for empirical parameters in 3 different metropolitan areas, and this has been a big job. More or less, you could say the division of work here is that Ian has dealt more with the analytical part, the formulas, and I have dealt more with finding the numbers for these 3 cities. So the 3 cities, I should say 3 metropolitan areas we have used are Los Angeles, Washington, D.C., and London. And we did that partly because we're just looking for a variety of conditions, cities that are quite different from each other, so that you can see how those conditions may affect the results. So the notation here makes this look more complicated than it actually is. These are just simple linear equations, as you'll see, perfectly common sense. And the notation, which is the same as in the written paper, if any of you have that, or if any of you want it, by the way, give me a card or something. I'd be happy to send you an email. It's also it's on my website, which you can find pretty easily at UC Irvine. So the I's and J's are just indicators to remind you that we are distinguishing between peak and off-peak travel and 3 modes. We're choosing auto, bus, and rail. We chose 3 cities that all have rail systems, and they all have pretty good data separately on the bus system and the rail system. That's sometimes a problem to get. I'm not sure in every case that we were able to get it exactly right. So when you think about the empirical implementation of this, 3 times 2, that's 6 different numbers for every variable that we want. So this is why and that's for each city. So it's 18 if you multiply by 3 cities. So you can see there is really a lot of many empirical numbers that are going into this, and that is making it difficult, I have to say. And even now, the results you're going to see, I would have to list as preliminary. Okay, so here's the subjective travel costs, the things that I was talking to you about that need to be added to the agency costs in order to adopt this idea that you could think of users and agencies in the same metric and add their costs. And fortunately, in most of these, there has been quite a lot of research in the first three specifically into how people value their time spent in the vehicle, waiting or walking. Crowding is a different story. There's been a little research on that. I've tried to finesse it in a sense by using an equilibrium conditions so that I don't have to measure it directly. However, I do need to know something about the elasticity of how crowding depends on the number of passengers in a vehicle, and that's where I'm less sure. So all this says MIJ here is the passenger flow, number measured as passenger miles. So this just says that for each type of operation here, each time period and each mode, there's a parameter which is not necessarily constant because it may depend on some other things, but it's going to depend, that parameter is just going to determine the amount of time that people are spending, or the crowding here, which is an abstract concept, but as you'll see, we don't really actually have to measure C. We only have to measure how it varies with things. So let's see. Yeah, actually, none of these constants do vary in the within the work that I'm doing. They might depend on other things. Like I've done other work where you change the highway system and change the amount of congestion on highways. So that, of course, would affect the time that transit vehicles are incurring. But in this one, we're just taking these to be constants. So now here's a lot of technical stuff, but it does have an implication. I mean, it has an effect on these results. So I just want you to know that it's there. I'm certainly not expecting anyone to take in all the functional forms. The time that you spend in the vehicle traveling, most studies have just taken that to depend on the speed. So that's the congestion function TI. TI depends on the aggregate vehicle flow of autos and buses, with buses having a factor applied to them. So that's just simple congestion. And then in addition, there's a dwell time. And this is a cost for transit passengers that goes up even if you expand the transit vehicle and so that people aren't crowded. You're adding the number. If there's more passengers getting on the vehicle, you're adding some time for them to get on, unless you also expand the number of doors. Then you would not. And I haven't really taken that into account except looking between between buses and trains. More doors, of course, get people on faster. So each mode has a dwell time per passenger, which plays a role. And that gives some incentive not to take all of the additional traffic by expanding the size of a vehicle, or just by allowing more people onto a vehicle. So then we have that's the in-vehicle cost. Then we have these access costs, waiting for a vehicle and walking for the vehicle. So waiting is W, walking is Y. And they are assumed to depend on the frequency of service, with some elasticity to be specified. Now, some of you may know there are commonly used models where people arrive randomly at a bus stop and they have to wait for half the interval between buses, which is known as the headway. And so then this elasticity would just be -1, because if you double the frequency of service, you'll cut the waiting time in half. But we allow it to be something else. More specifically, what we allow for is that if you have rather long waiting times, people will probably use a schedule. And there have been a few estimates of just how long people do actually wait at a bus stop as a function of what the headway is. So we allow for that, for not being just a single elasticity. Here we have route density. So this one, I think we did just make this equal to -1, if I remember right. So that's just how many routes you have within a given geographical area, and the more you put in, the less walking time there is to them. Crowding cost, again, this is still abstract, but as I said, what matters is how it depends on something. So what we're going to have it depend on is the load factor, that is the ratio between the number of passengers on a bus on average at any one point in time and the bus's capacity. And that's what you could expand. And so here's what happens. See, if you want to expand the bus capacity, make bigger buses, that'll of course cut the crowding costs, but it will add to the agency costs through this function here. So what this function says is that providing transit, first of all, there's some fixed cost in the case of rail, which we take into account, which you could think of as maintaining the stations. We're only dealing with the operating costs here. We're not, I should mention that right off the top, we're not dealing with the infrastructure cost itself. And it's not that you shouldn't consider that when you're building infrastructure, but we're just thinking at this point of how do you price the infrastructure that you have. So by infrastructure, I mean basically rail lines or any special busways that you might have. So we're assuming that rail does have some fixed costs. Buses don't, or it's small enough that we ignore it. But this is the variable cost, and we're assuming that it's proportional to the time. That is, most of the variable cost is going to be to the agency is going to be related to drivers or other people that have to maintain vehicles. That will be proportional to how much time those vehicles are on the road. And so that's why TIJ is here. That's the same as the user's in-vehicle time. And, of course, the total patronage expands that to give you, V is the vehicle service offerings. So this is just the time per vehicle times the vehicle service offerings. And the average cost of this variable cost component is going to depend on the transit capacity. That's what this function means. And that's what that last sentence basically means. So with this and a lot of arithmetic, you can derive the optimal transit price through the process that I described verbally at the beginning. That is, you create your cost function with the agency costs and the user costs as defined here. You find for a given passenger volume, you can find what the minimum cost is. That gives you a cost function. Cost is a function of volume. Therefore, you can differentiate that. You get a marginal cost, and you can set the price equal to the marginal cost. Now, of course, the marginal cost depends on the volume, so we have to iterate to get the volumes. So we have to add in, to get the final solution, we have to add in a demand function. So for that, we use measured elasticities of demand with respect to the full costs, including both the price, the transit fare that people pay, and their user costs. And that's how we finally get the numbers. But at this stage, it's just in terms of a formula, which will depend on the amount of passenger volume, and therefore, at this point, all we're doing is describing what that marginal cost looks like. And this is what you get if you take into all those things into account. And the reason it's complicated is that, as I said, we're trying to take into account a number of different rationales for transit pricing. So the components of this are the marginal supply cost. Okay, so that's pretty simple. You know, the first thing would be if it costs the agency an extra marginal amount to cover the passenger, which is basically going to depend on how much that they expand their service in response to additional passengers, then that needs to be covered. So this is all just implementation of marginal cost pricing. This one is the marginal external cost of travel time, pollution, and accidents. So basically, that's the automobile externality. Now, I said automobile externality as a way of motivating and simplifying. Of course, buses also have an external cost because they contribute to congestion. That's factored in here. Remember, there was an alpha in a term that showed you how congestion depends on the total amount of traffic. So buses are counted there. We even allow here in the formula for the possibility that that there's congestion on the rail network. That is, since we're dealing with a fixed infrastructure, the rail network could congest itself in a sense, and we would put that into this term, but we've set it equal to 0 in the empirical work, so I won't go into it. The third part here are intermodal effects. So, oh, by the way, this is just for peak rail. Just, you know, of all the 6 combinations of peak, off-peak, and the 3 modes, I'm just writing it down for one of them to show you how it works. Let me think. Okay, actually, I misspoke a minute ago because this term here was just the marginal external cost of peak rail. So that one would only account for the portion that if rail was congesting itself, or if it's causing accidents, or if it's causing pollution. And we basically set that equal to 0 empirically. This is the part that I just described that would take into account the effect that the operations of one mode have on all the other modes. And so basically, this MIJPR is the diversion ratio. So that tells you how much you're diverting traffic from the other modes. So think about automobiles, since that's where most of this comes from. So you do something with a transit price. You're going to divert some people off of transit. So we're dealing with a peak rail price, so we want to know how many people divert from peak rail to the other modes. So a certain fraction of them will go to automobile, which we've estimated. And for that fraction of people, what you're doing by diverting them is you're saving a certain amount of social cost because of these externalities. And so we call it net because it's not just the marginal external cost itself, but it's the marginal external cost that's not already internalized, that is accounted for by individuals through the prices that they're paying. What prices do people pay? Well, for automobile use, they have to pay a fuel tax, so that captures some of it. If you're talking about marginal external cost on another transit mode, or the same transit mode at a different time, then they're paying some through their why does that say subsidies? It should just be transit price, I think. That should say transit price. In other words, suppose I want to do something to the price on off-peak bus service because I'd like to draw people away from peak bus service because I know it's costly. It's costly in a number of ways, one of which is it congests the roads with all these buses during the peak hour. So I would capture that by the external costs that those bus passengers during the peak are imposing. A certain fraction of them get drawn to whatever mode I'm changing the price of. That's the MIJ here. But those people is not well, that marginal external cost is partly offset by the price that they're already paying. So if they're paying a price, that gets subtracted. So that's why that's net. Yeah. And then finally, the marginal user costs. And these are what I was calling the scale economies earlier. Here they're called external because, in a sense, one user is imposing an external benefit to others. It'd probably be better to not call them external, just call them the marginal cost of all of these different costs, all these different components of both users. And I've put, for convenience, one of the agency costs, that of larger vehicles, into that same term. Okay, so the first term refers to the mode itself, in this case peak rail. Third term is the other modes, all the modes besides peak rail, and the last term is all of the modes. So the dominant portion of the last term would be the users on peak rail, that is these scale economies, what you do for their convenience by making peak rail a bit more convenient. Now, I haven't said in this formula yet how you account for whether rail whether in order to handle the extra passengers, you expand service or you just let people crowd more. And so that's going to be in the next couple of slides. And actually, the next 3 slides. So I'll do the 2 extreme cases that I mentioned earlier, the proportional service adjustment and the no service adjustment. Now, to help you through those, I worked these out, but I'm not sure that I need it here. Let me try skipping this slide for now. I might need to come back to it. So I'll go right to the polar cases. Epsilon Vm is just the elasticity of vehicle miles with respect to passenger miles. That is to say, if you expand passenger miles by a certain percentage, what percentage do you expand vehicle miles by? If it's 1, that's the proportional service adjustment. If it's 0, that's no service adjustment. And the base case, I mentioned it. This comes out of a rather stylized version of this model where you simplify it a little bit, get rid of the dwell time and other things. When Mooring did his work, and he was not taking walking time into account, he was taking waiting time into account, he got something called the square root rule. You might have heard of this. And it basically says that you should expand service proportional to the square root of the population. So in other words, that epsilon would be 1/2. If you double the, well, if you add, say, 1% to your passenger load, you would expand your service by 0.5%. It turns out that when you allow for additional forms of adjustment, in this case, walking time, or in other words, the transit agency can affect walking time by increasing the route density, then you get a different number for that. You get a 2/3 power rule. So it's this would say that you should expand service proportional to the 2/3 power of passengers, which means that epsilon is equal to 2/3. And so that's what I'm going to use as a base case. It's not that that applies exactly to this model, and we finally gave up on trying to actually derive an optimal response for the transit system from this model because it's got too many pieces in it. But I think our reasoning is that we can cover the extremes of the results, and that this would be kind of a focal point for the results. So now I'll show you what these components that I mentioned I'll put it back on just to remind you. The components of the optimal price are these 4 parts. And the third one includes the second one. That is, the third one is the net MEC on other modes. So what I need to show you is what the marginal supply cost looks like, what the marginal external cost looks like, and what this MUC, marginal user cost, looks like. So in the case where you adjust service proportionally, that's my pen. This is basically the cost to the agency. And if you remember, I specified the cost as a cost per vehicle hour. So you have to multiply by the time in order to get the cost per passenger mile. So K times T would be the cost per vehicle mile. That's something that we can easily find in the statistics. And you divide that by the occupancy of the vehicle, the number of passengers on it, and that gives you the cost per passenger mile. So that's the marginal supply cost. So you see the proportional service adjustment is basically you're expanding. At the margin, you have to expand service fully to account for each passenger, and so it's the same as the average service cost or the average supply cost. The external cost, let's see, there's 2 parts here. Z incorporates accidents and pollution, and MCC is congestion, marginal congestion cost. That's applying standard models of congestion and how people value that time. So this is the congestion per vehicle. Again, divide by occupancy because you're expanding the number of vehicles proportionally. And then finally, because we're expanding service, we're cutting people's waiting times. You get more frequency of service, and so that comes into here. Now, the slide I didn't show you has the condition between whether the agency would increase the service frequency on a given route or whether it would increase the route density. And so given the model that I've written down, there's an optimization condition there that if the agency applies that, the two terms that you would get here, which include waiting time and walking time, combine to this. So in other words, actually I could have written this as this equals 1/2 of this and 1/2 of the same thing with walking time. So you would say waiting time and walking time, and it just turns out in this rather simplified model, those amounts are equal. So I can, and they have to be equal according to that optimization. So I can just simplifying it by writing it this way. So that's what I mean by this last paragraph. And then I'll have a very similar condition in the next slide, which will now go to the other polar case of no service adjustment. So this is polar service adjustment. If you think about no service adjustment, this marginal supply cost is 0, right? Because now we're saying when more passengers come to the agency, they don't expand their service at all. So it doesn't cost them anything. Of course, then it's going to cost the users something different. And so here's what that looks like. Supply cost is 0. The marginal external cost is now related to the dwell time because we're now adding more vehicles, more people per vehicle. So they're all slowing the vehicle down. The vehicle's spending extra time boarding these extra passengers. That has two effects. It has an effect on the passengers themselves. All these rows are the people's own evaluations of one of these components of user cost. So this is their evaluation of in-vehicle travel time because all the passengers already on the bus are having to wait while somebody else boards. So that's in-vehicle time. And this is how many passengers there are. Oh, ij, so that's why it gets multiplied by that. The K, if you remember the agency, and you can just think of this simplifying as just labor cost, the driver cost. So the driver is also being paid to sit there while an extra passenger boards, and that's what the K captures. So that's why this extra dwell time per passenger gets multiplied by both of those. This is not insignificant, this last term. And I think a lot of these models have ignored that. Certainly not all of them. The Belgians, I think, took that into account. But especially in the United States, when you have a lot of transit vehicles going around without too many people on them, and generally their value of time is probably quite a bit lower than the driver's wage, that driver's wage can be fairly significant. So especially in the off-peak cases, we're going to see that plays a role. So this marginal user cost is, so now that, let's see. Okay. There's no effect on walking and waiting here because we aren't adjusting the service. Okay, so we don't save any people there, so that doesn't enter. But now there's an effect on crowding and or using larger buses because we're going to put more people on a bus or a rail car. So let's think of it, bus. That would be where this would come into play more often. So again, there's an optimization condition on the handwritten slide that I didn't show you. The same kind of reasoning. You consider the agency's costs of using larger buses and the user's costs of crowding, and you add them up. You can see that those are going to offset each other in the sense that if you make the bus larger, you cost the agency something, but you save costs to the users. So you can find the point that minimizes that and build that into this. And then once again, there's an equality between a certain function related to the agency's cost, which is how I've written it here, and the crowding cost. So that allows me to take the crowding cost out of the equation and just represent it in this way. And so this is the cost to the agency, but it's it's divided by the load factor, just in order to get it in the right units. But you'll see this K2IJ, that was the parameter that told you how much extra it cost the agency to make their bus or rail car one passenger bigger in capacity. Okay, I think I can go to results, finally. The first one aren't the results. These are the input parameters. Oh, just a few of them. There's a table in the paper that's pretty complete. Perry and I are continuing to work on this, and there are certain times, we look at a result and we say, something's funny, there's something very strange about the cost for London Transit, so we keep going back and checking the statistics to see if we've done it right, because it seems to have very low cost. Does that show on this slide? Average variable agency cost, yeah. So now we've put everything in U.S. units in constant dollars. I think we're using $2,000, if I remember, maybe 2002. So this cost is cents per passenger mile, but you see it's lower in London than anywhere else for the most part, with a little bit of overlap between peak and off-peak. In the case of bus, not so much in the case of rail. And I have not figured out the reason for that. Maybe the pay scales are lower, but London is not usually thought to be exactly a low-cost city, and the rail costs are reasonably high. And these are just operating costs, so it doesn't have anything to do with building the rail systems. So we're continuing to explore some of these parameters. So in that sense, it's still preliminary. But some of these statistics, like passenger miles, are pretty solid. The initial occupancy. So basically what we do is we compute everything at the initial situation. So since the equations are all basically equations that apply to small changes, differential calculus, the initial point is the crucial one. However, we then do actually also iterate in cases where there might be a big change in the transit price. We allow the passenger volumes to change and sort of replace the initial occupancy by whatever results from that. That iteration process is another problem that we're still having with the paper. There's actually, with London, sometimes we're having a hard time just getting it to converge. And so we haven't completely solved that. So these are fares all per passenger mile, again, in U.S. cents. And so for London, for the UK, we're using a conversion rate that was the exchange rate between British pounds and U.S. dollars in, what did we use? We keep updating this. So I think maybe it's now 2003 is the year that we used for that. If I remember right, it's about $1.6 dollars per pound, which is a little lower than it is right now. Pollution costs, I won't try to defend this. They end up not playing a very big role, which is fairly common. A lot of people don't appreciate this about the economics literature, but the best you can do if you try to actually measure how much people are willing to pay to reduce pollution, it's a lot in aggregate, and you see that in our political system. But when you divide it by anything like vehicle miles or amount of fuel consumed or something like that, it turns out to be pretty small compared to the other things in this model. So the line I usually take out of this kind of analysis is when you quantify pollution costs, they're big enough to justify a lot of pollution control policy, but they're usually not big enough that you would expect them to justify big changes in people's driving habits. So you may or may not agree with that, and this isn't the point. I'm happy to debate it. I don't mean that. This is not the paper where I'm really trying to make that case. We're just using those numbers. And so they don't play a real big role in the analysis. And the same with global warming, which is even more speculative. For pollution costs, what you have to do is look at the mortality rates. Most of it turns out to be mortality. Your chances of dying from pollution are really small. So this is the good news. but they're not zero, and people really care about that according to the best studies that we can have, and most of these come from wage studies looking at wage premia that have to be paid for people in more risky occupations. So in a statistical sense, if you change somebody's probability of dying, let's say, from lung cancer by 1 in a million, they're probably willing to pay a few dollars for that, according to the latest estimates. So that, then, as you can inflate that up and talk about, say, $5 million per life as the value of life saved, which is not really the way, it's a dangerous way to talk about it, although that's the common term for it. But what it is people's willingness to pay to make small changes in an already small risk of death. So that's how pollution costs are mostly done. I mean, there's also more illnesses in there which play a lesser role. Global warming, you can just imagine trying to do this, but I'm not the one who does these studies. In the case of global warming, the IPCC, the International, I've got the wrong name, International Policy on Global Climate Change, I'm sorry, I can't think of the right initials, this huge international body of scientists that has multiple scientific agendas in trying to describe the whole process that leads to global warming. And there's one component of that that tries to assess the effects of global warming. And there's a component of that that includes some economists, but they're not just economists, that tries to cost it out. Now you're talking about effects that will occur in mostly, in 50 to 100 years, and you're trying to imagine how are people going to adapt, what is the world going to look like 75 years from now. So these are very speculative, there's no doubt about it. But the great majority of studies actually come out with numbers that, again, when you divide by the enormous number of gallons of fuel that we're using in the world, don't come out to such a huge number, something like 12 cents a gallon. I mean, it's not insignificant, especially compared to our gasoline tax. It would be a substantial change in the gasoline tax. So it's the same story that, I come out with the same story, my own conclusion out of this, that there's plenty of ammunition there to justify a lot of work toward greenhouse gas control. But what you're going to find if you optimize the way economists kind of figure it out in their models, that most of that work is not going to result in a lot of change in gasoline usage. This is a big disappointment to a lot of people. I myself have worked on the greenhouse gas regulations in California, and I'm a supporter of them. But you can't really expect that to be a major part of global warming policy. And in fact, the models that try to look at all of the sectors of the economy and see where greenhouse gas savings would come from, they mostly focus on the energy, on the electric power production, and it's especially coal. It turns out that you get big savings in carbon dioxide emissions by converting a lot of coal plants to natural gas plants. And it turns out that's just a whole lot cheaper to do it that way than it is to get it out of motor vehicles. So it's not that there'd be no effect on motor vehicles, but it's just not a dominant one. So the dominant one, which pretty much any transportation economists, I think, will come out saying the dominant factor with motor vehicles is congestion. And so you see the congestion costs are just way above the other ones. So although we've taken everything into account, or we've tried, mostly this is going to be a story about reducing congestion. And that tells you right away it's going to be a story about peak versus off-peak, because that's going to be much more important during peak periods. So we are going to get big differences in that motivation for subsidizing transit between the peak and the off-peak. So, with some hesitation, I'll put the results that we have now up. And it's kind of hard to say what to focus on exactly. But if you want to look at the bottom line, no, it's not the bottom line, sorry. The quote bottom line, the optimal transit price. Okay, here it's these four columns. Here's the optimal transit price in cents per mile. And of course, the average trip lengths vary from one to another, so this isn't exactly telling you just what the fare should be. And although for simplicity, we've done everything by dividing by miles, so everything per passenger miles. We're not making a statement that fares should or should not be proportional to distance. That's another debate, and really our results don't bear on that. So the fact that we did it that way is just to simplify it. So if you look at these optimal fares, well, first of all, I told you we had some problems with London, so they're negative. Now, this is not theoretically impossible. It could be that these externalities are big enough that you ought to actually pay drivers to get out of their cars and go on rail. Of course, the trouble is if you pay people to ride on rail, you just might attract a few people besides those coming out of their cars. In fact, way back when I was in graduate school, there was so this was in the 70s, there was a program called Free Transit in, I think it was Trenton, New Jersey, that they tried making it free as a kind of an experiment. And of course, guess what happened? Lots of teenagers were riding around the buses, joyriding, bringing their beers in, and so on. So that could have problems. So I'm kind of telling you what the theory is saying, not necessarily that you'd really want to do this. But also, I have some hesitation about whether we've got everything right that we would be getting such a big subsidy in the UK. But this does enable you to see where it does enable you to see where it's coming from, because the components are here. Let's see. We've got the change in net external cost to other modes. So, okay, here's the marginal external cost for the own mode. So that's not very big. This is basically for rail. I forgot why there's even anything in there for rail. Maybe I can't remember, but you see it's very small. For bus, you've got a little bit of pollution from the bus accounted for and some congestion. So that's why there's a factor there. It's not insignificant in the peak period. Now here's the net external cost to other modes. So most of this is coming from that congestion cost from highways. So in interpreting this thing, basically, the number of people that you're able to take off the highway by lowering the transit fare is reflected in this line. And this is telling you how much of the optimal reduction in fare compared to supply cost you ought to take for that reason. So you can see right away, like look at peak rail in London, for example. Supply cost 52 cents, but the external cost is 63 cents. So that's why you're getting a negative. It's saying the external costs are so big that if you could, you'd actually like to subsidize it by more than 100%. And of course, that's modified by these other factors, which are these scale economy factors, which turn out to not be as important. But in the off-peak, there is something there. And what that's reflecting is basically off-peak in most cities. London's got pretty decent transit service. You see somewhat bigger numbers in Los Angeles. And Washington I just didn't show because it wouldn't fit on the slide. Washington is somewhat similar, not exactly the same as Los Angeles. You have a lot of buses, especially running at pretty high headways. Large intervals of time between buses. And so the waiting time costs are pretty significant. And so if you make a small percentage change in that, that has a noticeable effect on people's cost, and that's what's being reflected in that line. So I guess the conclusion you could take from this is that in the peak periods, most of the rationale for the transit subsidies are coming from taking cars off of the congested roads. In the off-peak, it's a little more balanced. Some of it's coming from that. Quite a bit is coming from the waiting and walking time. The crowding just turns out to not really play that big a role, at least with the numbers that we have now. These other rows just tell you a little bit about how this first row, the optimal transit price, looks in relation to some other things. So this is how it looks in relation to the average cost. So how much do you have to subsidize in cents per mile? So you can see it's pretty big. So here now they're divided as a ratio. As a percentage. So this is telling you, for instance, in Los Angeles, that the optimal fare would cover less than half of the average operating cost. Only 22, 28%. I have several colleagues who probably aren't very happy with this result if they're aware of it. You know, a lot of transport economists are very skeptical about the use of transit for these purposes and about its effectiveness. But our model is showing, it's not really showing you how effective it is. It's just showing you that it's effective enough that it would justify quite a large subsidy. Or in other words, the congestion externalities are fairly large. And this relates it to the initial price. So by the way, the bold numbers are just ones that I thought were more interesting for you to look at. They don't have any special significance. So this is telling you that the optimal price that we're calculating would be a lot higher in these cases than it is now. Let's see. Yeah, that's right. And it's a lot lower than it is now in certain cases in London. And that's kind of all over the map, too. And I don't exactly have a story as to why the existing price structure seems to be so different from the one that we're suggesting out of this. So I'll be happy to put this back up if you want to talk about it. Let me just draw the conclusions that I have drawn and then kind of throw it open for discussion. Tentative, I will emphasize. And especially because I'm now generalizing over 3 different cities, and they don't. We hoped that they would tell a nice, really easy to describe story, and they don't. There seem to be a lot of pieces to the story. But generally, the optimal peak fares are pretty low, although, as you saw in Los Angeles, not as low as they are now. The optimal off-peak fares, it kind of varies from case to case. The main components in the peak are from automobile diversion, saving congestion. On the off-peak, I guess I would really say it's more like half and half of these two. You know, a little bit bigger effect of the own mode waiting time in cases where service is infrequent. And I said especially Los Angeles bus, if I put that back up here. See, that was this minus 16. So that's the biggest negative number. That is the biggest number that's working toward the direction of a subsidy in Los Angeles. Third is that the crowding and the cost of larger vehicles don't seem to play a very big role. What that says, if we're right about it, is that most of the transit pricing action, according to our model, should be in the consideration of user costs, of waiting and walking costs, and these externalities, especially congestion. And then finally, as I already pointed out, generally you get less than half of the operating costs for the optimal fare. So, oh, yes, I didn't say this before. Our operating costs, I said it doesn't include infrastructure, but it does include the vehicles themselves, and we just annualized the capital cost of those to get that. So this seems to provide an empirical rationale for reasonably high subsidies, even on just taking into account the operating cost for public transit. So let me give you've been too quiet. It makes me nervous. So let me give you your chance. Tony.
Your assumption is that the operating agencies actually optimize. But if you look at the actual operating costs, for example, you find the areas where the likely effect on congestion is greatest are the ones where they're subsidizing least. So, for example, the high-density routes tend to have a lower, the fare covers much higher percentage of the cost. And that leads into the second part of my question, which is how do you account for the argument that one of the effects of the increased subsidies is simply increased waste? There are a number of studies that have been done where you indicate that, in fact, rather than optimizing, what you end up doing is providing inefficient services that really don't provide much benefit.
Yeah. I mentioned that last point. First of all, one of the limitations of this is that we're aggregating over all the routes of the system. So we're not able to take into account if the agency is providing high density one place and low density another and that kind of stuff. And I would love to. Actually, if I ever get this finished, I would really like to do some work that's more disaggregated. I think we'd learn more from that. On the second one, how do you account for that argument? At this point, I mean, you could say we don't account for it, but what we're doing, you notice, although I described it as the optimal subsidy, what we really derived was an optimal price. And then we compare that to the current average cost. So I guess it's in that last stage when we compare to the current average cost, if I call it a subsidy, that's where we're building in the assumption that that average cost isn't going to change because of the subsidy. So I guess that would be the point where I would bring that argument in, would be to say, okay, if you believe the optimal price, which you see is based on other considerations, then how would you achieve this price? Well, if you mandate that the agency offer service at this price, then you've got another question: is how can they do that, given that that's below their cost? They'll have to have a subsidy in some form. But you could do the subsidy in different ways, and you could try to design it in ways that they couldn't use it to increase wages or in waste. So, I mean, one is the so-called user-side subsidies, where the subsidy is strictly based on like this amount per passenger, and so they have to offer a service that attracts the passengers in order to get the subsidy. This I think has been tried some in the UK. So the practical problem with doing that is that the agency that's designing the subsidy scheme would then have to have accurate information about what the pure costs are, untainted by these alleged inefficiencies that result from the subsidy program. So I haven't solved that problem. In other words, I haven't attempted to solve the practical problem of how to design a subsidy system that will get the result you want, which is a lower price to the customer, but still have good service and not increase the cost. Yeah. Yes?
Do you think that do you think your model could be used to identify the point at which the optimal transit price is so low that it's no longer worth the cost of fare collection infrastructure and the waiting for collecting, and you could make all kinds of savings of time?
Yeah, that's a good point. It could. What I think you'd need to put in would be, just a cost per fare collected to account for that. I think my guess is that more of the cost is in the time cost to the driver and the other users than it is in the actual fare machines and that kind of stuff. So I suppose what that would do is just change the dwell time. And we've got the dwell time in there. You could have that be two parameters, one with fare collection, one without fare collection. And that would account for that. Now, of course, you can also reduce that through some of the mechanisms that have started been using that people have started using in the rapid bus movement. Take Brazil, but also experiments around this country where they collect the fares off-site, which presumably is a lot cheaper. So that would be an interesting thing to do. Yeah.
In
Sure.
your crowding model, what I'll call your crowding model, you have dwelling time going up, and presumably that slows down the bus. And yet, if I heard you right, you're saying that you wouldn't be adding additional buses to account for that. But wouldn't that also affect people's waiting time as well? So if you're trying to hold their walking and waiting time constant, wouldn't you also have to add additional capital expenses if you're just crowding the buses and increasing dwell time?
Okay, let's see. Yes, I see what you're saying. Anything that slows down the bus means you'd have to have more buses to operate the same frequency. Yeah. I think you're right, and I think we just didn't take that into account. So I guess within the framework here, what we should do is say that dwell time will also increase the headways, the time intervals between buses, and that would have an additional effect. Yeah, thank you. We just forgot to put that in. Yes.
The idea behind the transit subsidies and increased service is to hopefully get people out of their cars and riding buses to decrease the external cost of driving. Do you think there's any significance to the effect on people who use other non-automobile forms of transit, like people who would normally walk or ride their bike instead of taking the bus because service is not available? For instance, in Portland, we
Yeah.
have Fairless Square, where downtown you can ride the bus for free. And I noticed that a lot of those buses are really, really crowded because ordinarily people would just walk the 8 blocks or whatever to go to the other side of downtown. But since the buses
Right.
are free and they're
Right.
very frequent, they just hop on a bus. And so
Yeah.
my guess is that would greatly increase the dwell time and the
Yeah.
time costs. And I was wondering if you thought about
It's a good point, and we haven't accounted for that. We did think about having another mode in the model, walking. Let me see. We do. Well, I guess indirectly we've got that because these diversion ratios that we have, if you attract 100 new people to rail, we've got these ratios to tell where they come from. And roughly we account for 90 of them. And then the others we assume don't come from the other modes that we're considering. So I guess that could be from walking. I mean, we haven't specified. So I guess we have accounted for it in that way. And so in the case of bus, yes, that should be accounted for. If you lower the price of bus, you're attracting new people, that's going to have all these dwell times implications, and some of that's coming from walkers. Now, probably what we haven't done, because we're aggregating over the whole metro area, we haven't accounted for how you, like within the city square, you might get a big effect that when you look at the whole system might look small. Which could have implications for exactly the kind of thing you're saying. Do you want to have a free bus, in one area? Yeah, that's one of the costs and benefits to weigh. Yes.
Coming from the standpoint of a student who's interested in where he wants to go with his career, I'm interested in how you specifically came upon the idea to work this model. Was this something that your colleagues presented you, or did it just dawn on you one day?
Oh, things never just dawn on me one day. They always come out of discussions. I spent a year visiting at Resources for the Future. I had a sabbatical from UC Irvine, and I supplemented it with a fellowship that they gave me. And so I had many discussions with people there, and they were just building, although it's mostly an environmental research institute, they were building a capability in transportation. They have a few people there who had already done work in transportation, and they were building a real model, not an aggregate one like this, but a model of the Washington, D.C. area with all of its streets and transit links and so forth in order to study policies of that. So we had a lot of discussions about Washington area policies, including transit policies and the desirability of expanding the highway or pricing the highway with a beltway, which is one of the things that actually is under consideration there now. So I guess these discussions just led us to talk about some of these issues. How much should you subsidize prices? And we know a little bit about the literature, but it didn't seem to give us an answer. And meanwhile, both of us knew about some of the modeling that other people have used to try to understand how you should think about an optimal price for transit. And we just thought, we've got different pieces. If we put them all together, maybe we'll get a clearer answer. That's about the most organized I've ever thought about the process of how we started this. Yeah.
Yeah, on the wait and walk time, the bus, or a lot of people will consider that not to be a cost to them. They will think of it as something beneficial because they can consider that as their downtime or time on the bus or train.
I'm one of those people. This is why I always have trouble. But I do research on travel demand, and it's very consistent. If you if you relate people's choices to the amount of wait time and the amount of walk time, as well as in-vehicle time and price of the various modes, they are acting as though most of them would prefer not to do that. So I can't understand. See, I'm exactly like you're describing. The time in the bus I use productively. The time walking to it I think of as healthy. But I think you and I perhaps are not representative of the whole population.
Well, that's probably more and more because, I mean, like on the train or bus, you'll see people either reading or being on the phone or conducting business, basically putting that time to productive use. So how do you factor that in?
One ought to see that coming up. You know, as we continue to study the factors in travel demand, if that's an important one, we should see it. We should see a reduction in the value of time. Particularly probably for those modes where it's convenient to do that. So you might see it more on rail than on bus, for example. By the way, I would expect to see it on autos, too. I haven't seen this show up yet in the literature, but now that people use cell phones and fax machines and cook their sandwiches and everything else all while they're driving at 70 miles an hour, maybe they realize that this is increasing some other risks, and so that's offsetting it. But you would think that that would reduce the value of their time, and it sort of worries me in the sense that maybe we'll never get rid of congestion because people are just finding other ways to use that congested time.
If walking and waiting time have positive values, then I encourage you to walk to a further bus stop, or maybe take the second bus that comes to your stop, and you'll get more of this.
I hadn't thought of that.
You addressed this a little bit, and you talked about the cost of tax subsidies, and there are pretty good estimates in the literature for the deadweight loss or the marginal external cost of tax subsidies. So why not include that within your model?
Yeah, that's a very good point. Actually, I've argued with my co-author about this. He's resistant for some reason, and I don't understand it because he's a public finance economist, and he's one who's really done a lot of work to understand these. Maybe it's because, no, I do know the reason. He says to do it right, you have to build it in a way that will make the model much more complicated. And that has to do with the fact that your earnings can be affected by your travel times. Like if you think about your commuting, you know, if something slows you down, this may ultimately reduce the amount of time that you work, and that's all gets factored in if you do the models that lead to these estimates of the excess burden of raising a tax. Those models depend heavily on the burden of a labor tax. That is the fact that that raising taxes discourages labor supply, and therefore people work too little. And so you can't decouple that entirely from the transport system. That's the argument. I'm sort of with you. Maybe I'll sneak this into the paper somehow and just say, well, if you put in 15% or something like that as a common estimate, that's what you'll get. Yeah, in the back.
First, my apologies for being late, but it was due to the Amtrak train being over an hour late. My question is related to those sorts of delays and what might be solutions or potentially solutions coming out of the work of your model. Today's delay is nothing compared to last week when we were 7 hours coming from Salem to Portland, and it should have been an hour and a half or so.
Ooh.
So they're very serious and very regular delays. The major cause seems to be the fact that the freight has priority, and so it's a longer train, and passenger service will be put off onto a side rail in Oregon until the freight can get by. My question is, so I missed the first part of your presentation, again, my apologies, but is there a way that your model can be used to leverage some solutions for this situation here? If not in the current form, some way in an adapted form, and how would you see additional components being added?
Yeah. I can only think of an indirect way in which this work would apply to that situation, and that's the scale economies idea. that people often compare Europe to the United States and say rail service is so great there, why is it so terrible here? And it's a fair question. And a lot of people stop there and say, well, we should just make ours like theirs. But Europe is a lot more dense than the United States, and therefore it's possible to take advantage of the scale economies that are in my model more easily in Europe than it is in the United States. And although we're mostly talking about urban transit here, the same thing would apply to Amtrak or intercity rail transit. So this is a discouraging answer because it says unless the U.S. Should develop population densities somewhere similar to Europe, which it has now in New York, but that's about all, it's probably never going to be economical for us to develop a European kind of rail system, which might be what's really needed to solve these problems ultimately. I mean, obviously these are problems that can be worked on, and I'm sure there are very competent people in Oregon who are concerned about it, but like the example you gave, separating passenger and freight rail, that's a capital expenditure that somebody has to weigh against what benefits you get from it. And in order for those benefits to be really big, we need more passengers. So it's kind of it's a chicken and an egg in one sense, but it's really, I think it ultimately derives from the lower population density in the United States. I don't know who hasn't spoken that has been trying. I wasn't counting.
How much thought went into the selection of your study areas, and did you consider any other study areas to apply the model to?
Yeah. Mostly we looked for areas that other people had studied so we'd have something to compare with. And the other one we considered strongly was Brussels. And I have a colleague who came from Leuven, which is 60 miles from Brussels. That's Kurt Van Denter. I think he was on one of the early slides. So I was all thinking, oh, this will be great. He'll get me the data. And he asked and went there, and he said, it's impossible. They don't have very good data on the Brussels transit system. What they have is all written in Dutch. And so we finally narrowed it to the other three. Let's see. I think, Keith, you're probably next.
Just actually a direct question. In terms of the bulk of your savings are from congestion relief, if you want to call it that, but you've got a very aggregate approach to life. What metric, how do you estimate how much relief there really is to the road part of this game? So I don't know how you do it without doing microsimulation or without looking at it very closely, and your whole study's hanging on that.
That's true. Okay. We did not actually develop a congestion function and take the marginal cost and do it that way, which it might have looked like from what I presented. That would be the consistent way. What we did instead, we relied on other people's estimates of the marginal congestion cost in the cities that we're considering. So like David Newberry at Oxford has done a lot of estimates of that sort for London. I and others in the United States have done similar estimates that we were able to apply to Washington and Los Angeles. So they come basically from somebody's aggregate or possibly a compilation of disaggregate models of congestion in those cities. That's only I don't know if that's a fully satisfactory answer because there's still clearly a lot of aggregation. And clearly one of the implications of this would be the results are a lot different in a center city than out in the suburbs. And that would be another form of differentiation that it would be nice to be able to handle.
So our clock there is actually slow, and we're about a minute from our 1:30, and the other group needs to, unfortunately, get back into the room. So before we thank our speaker and thank ODOT again for sponsoring our speaker, I do want to make an announcement for next week's speaker. We have another visiting scholar, Professor Jonathan Levine from University of Michigan, talking about the topic of his new book, Zoned Out, Regulation, Markets, and Choices in Transportation and Metropolitan Land Use. I hope we can see some of you there. And want to thank you again, Professor Small, for coming and joining us today, and to ODOT for helping sponsor your trip.
Well, thank you all.